Well, welcome, ladies and gentlemen. This is Mr. Bergman.
And it's Mr. Sam's.
Hey, Mr. Sams. How are you doing today?
I'm great, doing quite nicely. It's got a nice little snow coming down outside.
Yes,
it's very
indeed, up here in our mountainous place that we live in.
Yeah.
We are right here in the mountains of Colorado. And of course, today we're talking about thermodynamics.
Yes,
It's
thermodynamics.
kind of appropriate with the weather system.
Thermodynamics. See, I can do the crazy accent things like Mr. Bergman does too.
What did you just
I said thermodynamics.
That sounds like you ate a prune or something.
A prune?
Yeah.
I kind of like prunes actually.
Oh, it
They're
just
pretty good.
didn't sound right.
No?
You need some help. I don't
Yeah,
know.
my nondescript
Professional
accent
counseling?
doesn't.
You know,
work.
talk like this is how you talk. I think is yes.
Okay.
No?
Well, I'll keep trying. See what happens.
Hey, we want to talk about a new chapter today. Chapter 16, thermodynamics.
This is the easiest chapter of the year.
easy schmeezy. That's right. Thermodynamics. What's thermo mean?
Thermo, heat or energy-ish.
Heat or energy. So, folks, what I want you to do is I want you to write that down, that heat or energy is what thermo mean. And what does the word dynamic mean? It means motion. All right, so it's talking about motion. Can't write today. Motion is, so it's like think of it this way. It's the flow of energy. So
Yep.
thermodynamics is the discussion or the study of the flow of energy. Good?
Yep.
Okay, so now this is now podcast 16.1. We've got three big topics to talk about. In this particular chapter, we have a number of different topics. By the way, those of you in internet land, we should make a note here. What do these references numbers mean?
Those are the section numbers in the Zumdahl book that we use.
Yeah, this is Zumdahl's 6th edition of the textbook, of chemistry textbook, that you can purchase. So that's what these refer to, by the way, just for FYI. So we're going to cover these sections. So
Yep.
today we're going to cover the first 4 sections, if I'm not mistaken.
Yes.
All right, so what makes things happen?
Breakfast.
Breakfast makes things happen.
Yeah.
How's that work?
I don't know. It just makes me go in the morning. Coffee makes me go in the morning. You're the breakfast guy.
In what sense does it make you go?
It gives me energy.
Oh, okay. Gives
Yeah,
you
so
energy.
I put energy in because things tend to go to a low energy state. So my body wants to go to a low energy state, so I have to refuel it periodically. Coffee
Yeah.
doesn't exactly give me fuel. It just,
So that cup of joe that you have in the morning, okay, that gives you energy to go.
if I put sugar in it, yeah.
Yeah,
It doesn't really have many calories on its own.
That's true. You need the old C12H22O11, right?
Yep.
Yeah, I love that C12H22O11. It can be addictive a little bit. But that's not the only thing that happens. In fact, you know, when you put that cube of sugar into
Yeah.
that coffee,
Yeah,
it dissolves.
it does.
But why does it dissolve?
Because things like also in the universe to be more disordered.
What do you mean more disordered? How
Well,
does that work with this cube of sugar?
Well, the cube of sugar is it has this nice ordered crystal structure, and then you put it into the liquid, and it kind of falls apart into individual little crystals and then individual molecules.
So it kind of gets like spread out.
It gets
then.
spread out. Yeah, kind of like
Yeah.
stuff on my desk. I start out the school year with a nice clean desk, and 3 hours into the school year, it's piled up with junk.
3 hours.
Yeah,
It takes
about
that
how long it lasts. Yeah,
So your desk gets all kind of
yeah, and I don't have to do anything to do it. It just happens on its own.
All right.
Yeah.
Yeah. Okay. And this is called, actually, low energy is called, or the energy in this instance is called what?
That's enthalpy.
So we're going to be more scientific now.
A-L-P-Y. Enthalpy.
Enthalpy. N-T-H-A-L-P-Y.
There we go.
And then disorder, the measure of disorder is?
Entropy.
Entropy. So there's two big E words, entropy and enthalpy,
Yep.
that we need to discuss, and we will at length here.
Yeah.
And by the way, our background picture, we should make a quick note of that. The background picture here is like the galaxies and the stars. And what's happening?
The universe.
The universe. What's happening is to the universe is it's becoming more disordered.
Right. As
It
a
actually,
whole.
As a whole. It is more ordered. There are areas of order, for example, this star right here, whatever.
Yep.
But it is becoming more disordered as time goes on
Yes.
in the universe. Okay, so let's talk about a couple of definitions, important definitions. Now, what's spontaneous mean?
That's when I just decide to do something out of the blue.
You know, no, it's not. I mean, yes, it is, but that's not what we're talking about here. I thought we were teaching them chemistry.
Oh, the chemistry terms,
The
yes.
chemistry term,
Spontaneous, it's just something happens on its own. You just kind of set something up and it goes. Kind of like putting a ball at the top of the hill. It will spontaneously roll down the hill. You will not see a ball spontaneously rolling up a hill.
Okay, so take the ball, and it rolls downhill. Okay, I'm good.
The
with that.
ball rolls down the hill.
Yes.
See, I can do the
Or
Bergman
you know,
crazy
the
accents
sugar
too.
dissolves in the coffee.
Yeah. It doesn't spontaneously go into the cube. You have to do something to it
So you
to
can't
make it
just
do that.
leave out the coffee and it'll turn into a cube of sugar.
Right.
Not going to happen.
No.
Ever by itself.
It could, but statistically speaking, it's not. No.
Yeah. All right, and then we have this concept called entropy.
Yep.
Okay, entropy is a measure of the
The measure of the amount of disorder in a system.
Write this down, folks.
Okay, now be careful there. It's the amount of disorder. So if you increase entropy, you increase the amount of disorder.
So we can say the higher the entropy, what? The more
Disorder.
disorder.
Yes, and we're going to identify this with the symbol delta S. Delta meaning change, and S is our symbol for entropy.
Yeah, that little triangle, guys, means change in something. We've
Yep.
seen like delta T's before. It means change in temperature.
And enthalpy was delta H.
Yeah, you know, you should go back and write that down for enthalpy. Right on this, write delta H here, and for this one, write delta S.
Yes.
Okay, so higher entropy means more disordered, and we should talk about that in terms of the states of matter.
Yes.
So
it's all liquid
let's
gas.
do that real fast. Hold on while Mr. Bergman gets to his new thing.
Wrong one.
All right, we're getting
There it is.
There we go.
We're using a new program, by the way, to make this.
And so we're learning new things.
we're learning a few new
here.
things.
There are various different substances. Okay, there's
Solids.
And there's liquids, and there's gases.
Yeah.
So let's label this entropy. Now, who has more or less entropy? Solids, liquids, or gases?
Solids have the least amount of entropy because they are least disordered. They are the most ordered. They have nice, happy crystalline structures. Gases are the most disordered, so they have the highest entropy. Actually, the word gas is a transliteration of the Greek word chaos.
And so we could kind of do it like this. Gases have a greater entropy than liquids, and liquids have a greater entropy than the solids.
Yeah.
Remember, the solids typically are ordered structures, and if you had say a flask filled with a gas,
They're all over the place.
what you're going to find is a bunch of spheres. They're flying all over the place, going everywhere. And so they're not kind of in any particular pattern, and so that would be the issue.
Yep.
Okay.
All right, moving on.
All right. So now, why does this actually occur? Why does this happen? Well, the concept is something that we want to call a microstate. Okay, what's up with a microstate?
Well, this has to do with statistics. Where are the molecules, in this case, we're going to have some gases in here, where are they most likely to be most of the time? Are they like, if we have two chambers here, and in one side is a gas and the other side is completely sealed off, it's a vacuum, and then we open up that little stopcock in the middle, where are they what's most likely going to happen? Are they all going to stay in one side, or when this reaches an equilibrium, are they going to be evenly distributed
Someone do A,
throughout?
B, C, D. Actually,
Okay.
that's what I want to do. So if I've got chemical A, and they could all be the same, but we'll kind of put a little tag on the A, B, C, and D on this side, and we open up the valve, what you're going to get are some different options. Hold on, I'm trying to my stupid program. Okay, there we go. This is what I want. So let's think about this. We've got our two chambers here. All right, so we've got chamber, well, let's just say the left side and the right side, right?
Mm-hmm.
So let's, let me change colors here. All right, so on the left side, we could have A, B, C, and D. That didn't go very well. Oh, well. That's one option. What's another option, Mr. Sams?
We could have A, B, C on the left. Oh, and D on the right.
Oh, okay, good. I see that.
Okay.
Any other options?
I could do A, B on the left, C, D on the right. I could do A, C on the left and B, D on the right. Let's see what else. Let's go A on the left, B, C, D on the right. Okay, then we could go B, C on. Okay, we can go B on the left and A, C, D on the right.
And then we can go C on the left.
And A, B, D.
A, B, D.
D on the left.
and I can go D on the left and A, B, C.
Uh-huh.
And of course, you could take these right here and essentially flip them.
Yep.
So there would be 3 more options where we have B, C, D, A, C, D, A, B, D, A, B, C, and this is A, B, C, D. Now let's do the 2 2s, Mr.
Yeah, the
Sands.
2 2s. There's quite a few of these.
So we've got A, B, C, D, A, C. So let's think this through here.
So we could flip those if you wanted to.
Yeah,
or
so
we
we
could just start with the B's, whatever you want
let's
to
do the B's.
Okay, so we could go BC on the left and AD on the right. You could go BD on the left and AC on the right. And then we could go, let's see, we already did, yep, CD on the left and AB on the right. And I think any other permutation is going to be a repeat of any of those, just in different order. AB versus BA type of thing. Yeah.
And then, of course, we can have 0 on this side and A, B, C, D
Yep.
on the left. Now, the whole point of this is it's actually just a statistical option. Basically, you can either go 1 and 3, you can go 2 and 2, you can go 1 and 3, or 3 and 1.
You already did 1 and 3 at the top.
Oh, this is 3 and 1, sorry.
Then we could do 4s and 0s.
And then we can do 4 and 0.
Or 0
Or
and 4.
0 and 4.
Yep.
Now what you do is you actually tally these up.
Yeah, and I think we actually missed a few or repeated a few or something.
I think we did.
Yeah.
I
Anyhow, not comprehensive list, but you'll get the idea.
You get the idea. Here's the point is if you were to do the statistical method, I don't think we've done it right, you're going to get a lot more that fit this category.
The 2 and 2.
The 2 and 2.
Yep.
And then the 1 and the 3, you'll get quite a few. Or the 3 and the 1, it's the same number. And the 0 and the 4, you're only going to get one different possibility.
Yep.
Now, this is only with 4 molecules of gas in
Right.
our substance. If we jump to, say, a mole of gases, so if I had just a jillion, 1 mole of gases in here, then this number would become, essentially what's going to happen is it's going to go 50% and 50%.
Yeah, and that's going to be the most statistically favorable position.
So, and that's called a microstate. So the microstate that's most favored is the one that's most spread apart,
Yeah,
essentially.
it's also called positional probability. Where is it most likely to be positioned?
And so that's how we can understand why things spread out. This is kind of why do things go from order to disorder, because it is statistically the most probable
Yep.
arrangement. So that is basically the concept, and yeah, I think we're good on that.
Okay.
Possible arrangements, we did that on the other page. Okay, now we should talk a little bit about some laws.
Yep.
Thermodynamics actually has several laws. There's, you've learned law of gravity, and what's another law in science? Newtonian laws of motion.
Yeah.
First law of Newton's first law,
Yeah.
and second law, and third law.
Yep.
Well, there's also thermodynamic laws.
Yep.
Okay, and there's 3 laws: the
Uh-huh.
first, the second, the third law of thermodynamics. The first law is called the law of conservation of energy.
Right.
What's that?
You can't create or destroy energy. The amount of energy is constant. You can transfer its form, but you cannot create or destroy the energy. Now, this is a little sketchy when you get down to the nuclear level, but as far as chemical terms goes, this works.
So you can't create or destroy energy. You can only change its form.
Right.
So, for example, when you drink that coffee in the morning, and you have
my
that
sugar in there, that's got chemical energy, or it's got energy stored as potential energy in the chemical bonds of the
right?
sugar.
And then, of course, when you eat it,
I eat
or
it.
drink it, I should say, and
Yep.
whatever.
It goes into my body. My body breaks it down. It turns it into other forms of energy. It pretty much transfers it into heat energy that my body gives off, and then another form of chemical energy.
Or possibly mechanical energy,
Or mechanical
as you
energy
move your
as I run,
body,
right.
as you run or walk or whatever.
Exactly. And then I can do stuff. I can lift a chair up, or I was
Yeah.
going to say lift weights, but I don't really do that. So
I lifted weights this morning.
Well, yeah.
Yeah.
I slept in this morning.
Yeah. Actually, I slept a little bit. I was going to ride my bike, but I'll do it this afternoon.
Yeah.
I know it's snowing. I'll ride it on a trainer because
Yeah.
it's snow and ice out there. Okay. Another important thing to understand about
Yep.
heat: it always flows in one direction. It
Hot
can never,
to
ever,
cold.
ever go
Or
in.
higher heat to lower heat. There's really no such thing as cold. It's just less heat.
So yeah, good point. Yeah, and so maybe you've probably heard this story, but if you have a house and it's a cold day, like it is right now outside where we live,
A less warm day than usual.
a less warm day, and you open the door and your mama says,
You're letting the cold in.
You're letting all that cold air in. Would you please shut the door? Now, with great politeness
Mother.
and with respect, you need to inform her that she's...
Yes, Mom, we are not in fact letting the cold in. We're letting the heat out.
You can never let the cold in. You can
Don't
only
sass
let
your
the heat
mama.
out. But don't sass your mama. If you sass your mama, you got to answer to me. And I lift weights. Okay. My voice is going away, though. That's not good. All right. Second law. What's the second law? Systems that have an overall tendency to...
Increase the entropy. That means they're getting more disordered. We talked about that a little while ago.
Yeah, so we have discussed this already, I think. So we need to... This is a couple of examples, of course. Mr. Sam's talked about his desk getting more disordered. Possibly, just think about, ladies and gentlemen, your room.
Yeah.
You probably have a room you live in. You've got your bedroom, and my guess is it's a disaster if you're like any teenager I know. And I have a teenager at home, and so the room has become a disaster. And it doesn't take, if you don't put the energy into it, it becomes a disaster. And
Yep.
you know it's true, etc. But that's also true of that cube of sugar. When you take that cube of sugar, you drop it into some coffee or some water, whatever, it breaks apart into many. It gets spread apart and becomes an aqueous substance, and that is also a demonstration of the second law of thermodynamics.
Yeah.
Okay.
So actually, in the Sumdahl book, they sum it up really nicely in the back of the book. They say the first law of thermodynamics says you can't win, you can only break even. That's the law of conservation
Oh,
of
I
energy.
like that.
And then the second law is you can't break even. Because it's always going to go to more disorder, and you're going to have to put more energy back into the system to get it back the way it was.
There you go.
So it's kind of like Murphy's law of thermodynamics. I mean.
Yeah. Now, hey, free energy.
All right. I like this stuff. I like free energy.
It's so cool. Free. It's free. It
It
doesn't cost
is.
anything.
I like free stuff.
Actually, free energy is an interesting thing in terms of its definition. It's the amount of energy available. How do I say this?
Yeah, available to do work.
Yeah. I think I misspelled that. Oh, well. To do work. So it's the amount of energy that's sort of freed up to do stuff.
Yeah.
So, yeah. Now, there's like this, in thermodynamic world, there is like this uber important equation.
Yes.
If you don't get anything out of this equation, well, there's two important concepts here to understand today. But this equation, delta G is equal to delta H
minus
T delta S.
S.
So actually, it's really a function, delta G. And free energy, by the way, did we say this? Oh, free energy is delta G.
Yeah.
Equals.
It's sometimes called Gibbs free energy. That's where the G comes from.
Yeah. Let's write that down, Gibbs. Some dead white guy, I think, was Mr. Gibbs. And so delta G is actually a function of delta H and delta S. Remember, delta H is that enthalpy, and delta S is what we were just talking about just a minute ago.
Entropy.
Entropy.
What's T, Mr. Bergman?
And what is T? T, of course, is the Kelvin temperature.
Must be Kelvin.
If you convert it in Celsius, you're wrong.
Yep.
Don't do that, please.
Nope.
You must work in kelvins. And
Yep.
so you must always have that going for you, otherwise you're host. And so basically you can calculate delta G based upon the other two. So, yeah. The fundamental properties or things that matter in the world are the delta H and the delta S. But the delta G is then how you kind of smoosh them together, I guess, is the way to think of it. And there's an equation, mathematical, so if we knew a value, number for delta H and a number for delta S, then we could solve the problem. Now, probably the most important table that you're going to see in this particular deal here. I should have made those white now. Let's kind of make the table a little easier to see for the podcast people. Okay, is the signs of the delta H are really, really critical. What do I mean by the signs?
The positive or negative sign.
So we've got positive here and negative here. And so if delta H is positive, what do we know about that?
It's endothermic.
What's that mean, endothermic?
And that means heat is going into the system.
So energy in.
Yes.
Okay, and then if it's negative...
Exothermic.
Now, folks, you probably should know this from previous chapters, and this is energy out.
Yes.
Give me an example of an exothermic process.
Burning fire.
Yeah. So I lit a fire this morning at my house. It was a cold morning, and so I threw some logs in the fire, and so energy is leaving the wood.
Yep.
And when it leaves the wood, it releases it into my house. So from the perspective of the wood, it is exothermic. And actually, from my perspective, as the person who is receiving the heat, it's sort of endothermic.
Right. So yeah, you got to be careful of what you're defining as your system and what is defined as the surroundings.
So an example of an endothermic process, one that you may not think of, would be you ever been
Boiling
to
water.
Yeah, I was thinking of something else, but that would work too. Boiling water, it takes energy in, right? If you've got a
energy goes into the water in order to make it go from a liquid to a gas.
So yeah, so if you want to boil water, right, you got a cup of water, and you have to add energy, right, to this to cause it to boil. The example I was thinking, you ever been to a one of those caves? Up here where we live, there's this place called Cave in the Winds. The Cave of the Winds.
Cave of the Winds,
Cave
yes.
of the Winds. And if you see up there, they've got all these huge stalactites and stalagmites. I can't remember which is which.
Well, the tight ones hang tight to the ceiling, and
Oh,
the
so
bottom
this
ones
is the
might reach the ceiling.
tight one.
Yes.
Okay, so the stalactite, what's happening is, of course, it gets very cool in those caves, and as it gets cool, endothermically, it produces these amazing things at Carlsbad Caverns, or maybe those people on Internet Land have caves nearby them that they can kind of see, and that's also an endothermic process. Now, delta S is the signs also matter, and I think we've already alluded to this, but it's good to put it in a table. If delta S is...
There's our bell.
Yeah, well, there's a bell. We're in a school, so yeah. Delta S is positive. It's going to become more
disordered.
So it makes sense,
Yes.
right? And then if it's negative, it's more ordered.
Or less disordered, whichever way you want to think of it.
I'll say equals less disordered.
Kind of a double negative there, but if you're thinking in terms of us being disorder, then it is less disordered.
And actually, the example of the stalactite thing that I just gave you just a minute ago, it came as a solution. It was one drop of a liquid at a time. As it came down, it produced. So it did get more ordered. So this actually would have a what sign for entropy?
That would be a negative delta S.
It's a negative value of delta S because it's getting more ordered.
Right. Now, earlier we talked about things like to be more disordered, but things can become they can become less disordered if
you have lower energy.
Right, if the delta H term kind of overrides the delta S term.
You'll see
we'll talk about that when we get back to that equation.
Yeah, and then delta G, this is very important to understand. If it is positive.
Work is done on the system.
So we would say it is not spontaneous.
Right.
That means it will not happen by itself.
Right.
And of course, then the opposite of that, if it's negative, it is spontaneous.
Happens by itself. Energy's going out.
So, dissolving sugar, is that going to have a negative value of delta G or a positive?
Well, that was a spontaneous process. I put it in and it happened, so that is going to be negative delta G.
So, folks, if you see something that just happens by itself, delta G is always going to be negative. And that's it. You don't have to overthink that.
Nope.
I saw it happen. Okay, delta G is negative. You see a chemical reaction take place, and you see a precipitate form in a chemical reaction.
On its own.
It happened.
Without any outside
Delta
intervention
G
of energy.
is negative.
Yes.
Okay? It's simple as that. Another sort of interesting that's a little bit different that is related to temperature that we could think about is water freezing and boiling. So if I take water, solid, and I go to water, liquid. Okay, outside right now, I would guess it's 20 degrees Fahrenheit outside, probably negative 6 degrees Celsius for you. What's happening to that water spontaneously?
It's going to go from a liquid form to a solid form.
So actually, it's spontaneous in this direction, isn't it?
At that temperature.
At the temperature that is outside.
Right.
However, I took some of that ice and that snow that's outside and brought it into this room where it's, probably 20 degrees Celsius or 70 degrees Fahrenheit. The process is spontaneous in this direction.
Right.
So it's dependent upon the temperature whether this is going to happen.
And that goes back to the equation. Delta G equals delta H minus T delta S.
So depending on the temperature, that affects whether it's going to happen or whether it's not going to happen. Make sense, guys?
Yes, it makes sense. Did you like that accent that time?
That was very good, very good. You still have some work to do, I think.
I see.
All right. Now, one thing we didn't talk about on that table, there's a sort of a special spot for delta G. It can sometimes be equal to 0. It could be positive or negative. But what happens at 0?
At 0, the system is at equilibrium.
And if you recall, if you've been following along on our podcast, you understand that we have just finished our unit on equilibrium. But guess what? We're not so done. Because you see there's a connection between delta G and equilibrium. Actually, it's delta G equals...
We'll actually come back to it.
No, we have to write it down right here. Delta G equals RT log K.
Oh, I can't remember the equation off the top of my head.
Yeah, that's what I was trying to think. All right, Mr. Sims is going to do that. It's negative RT. I'm almost positive. Negative RT.
ln of k.
Natural log of
Yeah,
k.
I think you're right.
That's
I'll look it
negative,
up.
right?
I'll look it up just.
We ought to check
I'll
that
double
just
check.
for
Why
fun.
don't you keep going and I'll double check the equation.
All right, we'll come back to that. Okay, so now we want to do a sample problem. And hold on, let me. Hold on, guys. Mr. Bergman is jumping, I know, a little bit. No, I don't want to stop. I'm learning how to use this new program, guys. Sorry about that.
We're not sure where the pause button is on the
I'm
new
trying
program. We want to pause
I'm
it.
trying to pause
Sorry.
the program, and so you should just pass forward.
Delta G equals negative RT ln of k.
Am I good or what?
You're amazing.
I am
Two
so-
amazings, in fact.
So that means if you know delta G, you can mathematically solve for k.
Right.
Vice versa.
Yeah.
If you know k. Now, by the way, R on this is 8.3145, and that's joules per Kelvin mole.
Right.
So you're not going to use the 0.0821 because this
we're
has
in
to do
joules.
with energy. And that's an important, by the way, this is in joules. By the way, oftentimes delta G is oftentimes given in kilojoules, and you can't use kilojoules and joules in the same equation. You'd have to convert one to the other.
Yep.
Typically, I convert the kilojoules into the joules to do this particular problem. All right, let's see if we can figure out
But this is not one of those problems.
this particular question.
Yeah.
Where are we supposed to end at, Mr. Sams?
I think after this one. After
Oh, okay.
The next table.
So
Yep,
what
we're
is the
close.
boiling point of a solution where the heat of vaporization is such and such, and delta S is this and such?
Right.
Well, we're going to use our equation. Delta
Delta
G,
G.
equals delta H minus T delta S. Now, when you are at a boiling point, you have call it substance X, and it's going from a liquid, and it's going to substance X and going to a gas. Now, I put double arrow, though, because, of course, you could boil it or you can condense it. And so when it's at its boiling point, it's at
an equilibrium state.
It's at a
because
state
both
of
the liquid
equilibrium.
and the gaseous forms are present.
So therefore, delta G equals
0, because we're
Zero.
at an equilibrium there.
So if we say 0 is equal to delta H minus T delta S,
Yep, and we're solving for the boiling point,
and
which
we
is a
add
temperature.
delta TS to both sides, then we're going to say delta TS is
T
equal
delta
to
S.
T delta S is equal to delta H. So if I say, let me go to the other screen where it's easier to work problems out. All right. Why am I not in a full screen? There we go. I'm good. All right. So if you can say T delta S equals delta H, and if you divide both sides by delta S, then you can say T equals delta H over delta S. Now we can just plug these
Plug them in.
Now it's not totally true.
Right. Delta H was 23.5 kilojoules per mole.
20, what again?
23.5 kilojoules per mole. And delta S is 34.5 joules over k mole.
34 and a half.
34.5, yeah.
And that's joules per Kelvin mole. But what's the problem here, Mr. Sams?
Well, we have kilojoules in delta H and joules in delta S.
So we have an issue here with the kilo and the joules.
Yep.
So if I want to convert this to joules, I can just times it by 1,000. All right, so I can say that delta H over delta S will be 23,500 kilojoules per mole divided by 34.5 joules per Kelvin mole.
And that's not kilojoules per mole on the top, it's joules per mole now.
Oh, thank you. I knew that. I did it right, but I didn't put it correct.
Yep.
Now, what you get to happen here, ladies and gents, of course, is the joules are going to cancel.
Yep.
And so will the moles
Yep.
cancel. Since this is actually on the bottom, in terms of Kelvin,
It's in the bottom of the bottom.
the bottom of the bottom, you will get it on the top, essentially. So what number do you get when you divide those terms?
681.
681 Kelvin. And if you wanted to convert that to Celsius, you'd subtract 273.
408.
And so you'd 408 degrees Celsius. I don't know what chemical this is. That's a pretty high boiling point.
It is.
But for whatever it is, it doesn't matter. That's what it is. Okay? And
All right.
I think that's it.
That's it for problems. We got a couple more little conceptual things.
Yeah.
This is a very important concept here.
Oh, yeah. Now, if you have an element, what's an element?
An element is
Like
something from the periodic table, like
carbon.
oxygen, carbon.
Carbon,
Yeah.
okay. What does it mean when they say standard state?
Standard state is in the state that it's in at standard conditions.
What are standard conditions?
Well, it's different than STP, actually. It's actually room temperature and 1 atmosphere. For some strange reason. I don't know why that's different, but...
I do, actually.
Well, why is that?
So if you're at standard conditions in a thermodynamic world, it is 1 atmosphere and 25 degrees Celsius. And you say, well, I've learned about STP, and it was 1 atmosphere and 0 Celsius.
Is that just gas law physicists like to work outside in the cold?
That's exactly right. Actually, well, not necessarily. But the point was, is the thermodynamic chemist is a different branch of chemistry than the people who study gas laws. And actually, you used to do gas laws, and they kept the standard temperature pressure was 25 degrees Celsius in 1 atmosphere. And then some point along the line, they said, oh, 0 would be easier for everybody, so they switched everything to 0 degrees. This is in the 1950s or 60s. And then, but the thermodynamicists, they said, we are not going to STP being 0 degrees Celsius. So,
Phooey on you.
phooey on you.
All right.
So, but carbon, for example, is a solid at room
Yep.
temperature
Yep.
at 25 Celsius. So therefore, it's in its standard state. And the value of delta H for this, and actually we call it the delta H
F.
0,
Oh, yeah, that.
would be 0
0.
kilojoules per mole. Always, if you have an element in its standard form, it's 0 kilojoules per mole. And by the way, that little 0 right here, this little looks like a degree sign or naught or whatever you want to call it, is means at standard conditions, meaning
right.
1 atmosphere and 25 degrees Celsius. So if I have fluorine gas, now I read F2.
Right, because that's how it exists.
It doesn't exist as F, it's F2. Delta H for this is 0.
0.
Actually, delta H not. Or if I have, I don't know, uranium. Now let's take mercury.
Oh, yeah.
Mercury is in this room would be a liquid. If
Liquid.
I had some, you can't have it; it's illegal. We have
And
some.
maybe not this room. It's kind of cold in here today.
Yeah, and then of course, what would delta H not be?
0.
0. What about this one? How about NH3 gas? So that would be equal to 0 too, right?
That's not an element.
Oh, you're right. You see, it's not an element, so it is a compound.
Right, so
it's
that one
delta
we're going to
H.
have to look up in the back of the book.
You're going to have to find
in
it.
the appendix.
Yeah, usually you'll find a table and have a list of this. We do not know this number.
Yep.
We could look it up and find
Yep.
it if we wanted to.
By the way, on the AP test, if delta H is supposed to be 0 because it's an element, they're not going to tell you that. They're going to assume you know that.
Yeah.
And some people go, I don't have enough information to solve the problem. Yes, you do. It's 0. Something's going to be 0 if you don't have enough information.
So the
Go back
AP
and look.
test assumes you know this answer. If
Yes.
you do not know this answer, then you're going to really have a hard time.
Yep.
You know, when you're doing it in class, you're going to look it up in the book and say, well, it's 0.
Yeah.
Because you're going to have the book with the table. But in the AP test, they do not give you the table. So watch that. All right, let's talk ourselves through this whole
Yeah,
process here.
this is key.
This is very important. If you understand this, you're light years ahead. Okay, so let's talk about delta H and delta S. Let's do positive, positive.
Okay.
I don't know. There's lots of choices first. So what does that mean, positive, positive?
Positive means it's endothermic
So endo and
and more disorder.
more disorder.
Yeah, so we're putting heat in and it's getting messier, basically.
Yeah, that's a good way to think of it. Is this gonna happen, Mr. Sands?
I'm going to say let's look at the delta G equals delta H minus T delta S.
So let's go back to our other screen here where we have just a place to write. So if delta G equals delta H minus T delta S, and this value is positive,
Yes.
and this value is positive. Now the temperature, what's that going to be, positive or negative?
That's always going to be positive because we're dealing with Kelvin temperatures here.
So temperature is always positive
Right.
because it's a Kelvin temperature scale.
Yep.
Remember that. So if I take a positive number minus a positive number, what do you get?
It depends on which side's bigger.
That's right. You see, because sometimes it can be positive or negative. So if this is the big side and this is small,
And this is going to be dependent upon temperature, by the way, because delta S is always smaller than delta H. So if you have a big temperature, then this will be spontaneous. But if you have a small temperature, it will not.
so when I say small, I'm talking about small and big. The only one that's going to change, frankly, guys,
Right.
is the T here. And so if this is big and this is small, then you get a positive number.
And that's not spontaneous.
And it's not spontaneous because positive is not spontaneous. So
Right.
you get small here and big here. And the way to get big here is actually to have a
Higher
high temperature. Then this will be negative.
Right.
Okay, so if we go back to our screen here, so if this is true here, this can be either
Yep. It'll be
positive or negative.
right. It'll be
And this will be
positive,
spontaneous. It'll be
spontaneous at high temperatures.
at high temperatures.
Yeah.
the example we just talked about a minute ago, if I brought some ice in from outside,
Yep.
it is spontaneous
At high temperature.
at high temperatures. Now, what does that mean, high, though?
It depends
It's
on the numbers.
not that hot in here.
No. It just depends on the numerical values of delta H and delta S, and it's going to vary from problem to problem.
Yeah, it's important to
So
understand.
it's kind of a relative term, but
Yes.
just know that if something's not spontaneous and you have a plus plus for H and S, if you increase the temperature beyond a certain point, it will become spontaneous.
That is correct. All right, let's do negative, negative.
Yeah.
Now, by the way, negative would be exothermic.
Yep.
And this would be
More order.
order. I'll just write order, okay? And so now if we go back to our other chart here, so if we say, I'll do it again maybe,
Yeah.
delta G equals delta H. You should write this down, I think, on your paper somewhere, guys, not just fill out that chart.
Yeah.
And so if this is negative and this is negative, okay, remember the temperature's positive.
Always.
Okay, so if this is negative and you subtract a negative minus a negative answer is like
Negative
plus a
plus
positive. So if you have a high, so let me think about this. So this is, if this is big and this is small, but this is plus a negative,
It's minus a negative.
minus a negative.
So it's plus a positive. So it's spontaneous. If
And
that's big and that's small, then delta G is negative.
And this is spontaneous. And if
Yes.
this is small and this is big,
Then it's not.
it's not spontaneous.
So again, this one depends. Now this time, it's the opposite.
Yeah.
So the positive positive, it's spontaneous at high temperatures. The negative negative, it's spontaneous at low temperatures.
So this is spontaneous at low temperatures. And actually, a good example of that is one I talked about just a bit ago, and that is the stalactite stalagmite here. This is spontaneous at low temperatures. Okay, but it's getting more ordered, hence the negative value of the delta S. Right. And the delta H is negative. Yeah, because it's getting, the reason, because it's going to lower energy. That's actually why it occurs. Okay, now the other two are easy, actually. If we do positive and negative, okay, positive, of course, is endo, and this is order. So if you're getting more lower energy, and lower energy and more order, if you go back to our mathematical equation, all right, delta G is delta H minus T delta S. Did I do positive, positive?
Positive negative.
Positive, negative. Positive, negative. If you
Yep.
take a positive number minus
Minus
a negative number, it's
That's
plus a positive.
Plus a positive. So that will always be delta G positive, meaning non-spontaneous.
There are no examples. It will always be positive. There's no either or, and it will not happen. It is not spontaneous. So this is something that's not favored in the universe.
Right. If you think about it, you're putting energy in both ways. You're putting energy in terms of delta H, which is your heat, and you're putting energy in terms of organizing it. So, yeah, you're not getting anything out. It's not going to happen on its own. Exothermic, heat's going out, and it's getting more disordered. It's messy. Those things are the things, the way things tend to go in the universe. So this, I'm going to expect to be spontaneous.
All right, so if I've got delta H and T delta S, so if it's negative here and positive here, a negative minus a positive will always
Be
be a
negative.
negative. So this will always be negative, which means it will always be spontaneous. All right, now you can think about it mathematically by looking at these things right here. And that's easy to do,
Yep.
right? But I also want you guys to think about this conceptually. The universe favors, write this down, guys. What does it favor? In terms of
There's things going to low energy.
delta
so
H negative.
and things getting more disordered. Delta S positive. So if
So-
those both happen in conjunction, it's going to be spontaneous.
Yeah, if you've got two factors. If they both work together, it's always spontaneous. If they both work against you, never
Never.
spontaneous. And if one's working for you and one's working against you,
Depends on
that's
the
the positive positive or the negative negative one, then you have to think about it. It depends on the temperature.
Yep.
Like the ice melting or the stalactite forming or whatever. It depends upon those factors.
Yeah.
So that hopefully this is very important to understand this from a conceptual perspective. That on the AP test, it's actually more important to understand this conceptually than mathematically. The second podcast is about the mathematics, and so so I change the color and we can do smiley faces or something like that.
And I can talk in ridiculous accents again.
I'll get you spiked hair.
Like Mr. Berkman does.
You must talk with a funny voice so that you can be stupid. I don't know, or silly, not stupid. I'm not stupid. I hope I'm not stupid.
I don't know.
I don't know. Okay, all right. We will see you
Bye.
in the internet land, or possibly, most likely, in our class, and then we can really hassle you.
Yeah.
So make sure that you always write your charges, Lee. I know that you didn't write that charge. All right. Don't forget positive and negatively. I know you. Your boy Lee. Sometimes he doesn't always listen. So all right. Have a nice day. Bye.
Bye. F10.
I think it's F10.